So in this video, let's talk about the ratio test. And the idea is that we're going to take a limit as n approaches positive infinity of an plus 1 over an, which is equal to some value p. And if p is greater than 1, then we say the series diverges. If it's less than 1, then it converges. And then if it's equal to 1, then we have no conclusion. And so we have to use some sort of different analysis. Okay, and so we're going to break down what this means. Well, let's look. Well, if we're given this series here where we have n is equal to 0, that goes to positive infinity of 3 to the n power over n factorial. Okay, now a good kind of tease with the ratio test is that these usually include factorials. So once you see a factorial, you should be thinking of ratio test. Not all the times, but most of the times. Okay, and so the idea is this is an. Okay, and so if I want to get an plus 1, everywhere that I see n plus 1 at, and everywhere that I see n, I'm going to plug in n plus 1. And so the idea is that I'm going to take a limit as n approaches positive infinity of an plus 1. So this will be 3 n plus 1, because for n we plug in n plus 1. And we're going to divide that by n plus 1 factorial. Okay, so this is an as currently constructed. Now we got to divide this whole an, and this is an plus 1. So we're going to divide this whole an plus 1 divided by an. Well, if I divide a fraction by a fraction, I could also multiply by the reciprocal. So essentially I'm multiplying by an now, which is the original function. And well, not function, but the original series, which is actually 3n over n factorial. But again, because we're dividing by a fraction, we're just going to take the reciprocal. So if we take the reciprocal, this becomes n factorial over 3n. Okay. And so the idea now comes down, now we got to cancel out. So if I look at this, well, n factorial, that goes to 1. If we cancel n factorial, n plus 1 factorial, we still have an n plus 1 here left. Okay. And for this, we have a 3n. So I'll cancel out a 3n. Okay, and for this, if I cancel out a 3n here, I'm left with 3. Okay, so in this case, I'm left with 3. And a lot of you guys will wonder, how does this happen? So let me rewrite this. 3n plus 1 is also equal to 3n times 3 to the 1 power. Okay, so same base, we add exponents. And so if I divide this by 3 to the n, my 3 to the n cancels and I only have 3 left. So that's why I was only left with 3 there. And so you could see that the only thing that left over is n approaches positive infinity of 3 over n plus 1. Okay, now we know this limit is 0. Okay, this limit will eventually go to 0 because this is a bigger number. We have something staying constant. The numerator constantly gets bigger and bigger. So this limit is actually 0. So we know 0 is less than 1. So therefore we can conclude that the series actually converges. I'm sorry about that. Series converges because it's less than 1. 0 is less than 1, so it converges. So in this case, we know that a series actually converge. Okay, so let's look at another one. So what if we're given this series here where we have n is equal to 0 to positive infinity of, let's say, n factorial divided by 2n plus 1 factorial. Well, again, I'm going to take a limit. So I'm going to take a limit as n goes to positive infinity of an plus 1. So everywhere I see n, I'm going to plug in n plus 1. So if I look at this, this becomes n plus 1 factorial. I'm going to divide that by, well, this becomes 2 times n plus 1 plus 1. Okay, and we divide this by an, which is the original series. So it becomes n factorial divided by 2n plus 1 factorial. Okay, so simplifying this, we know this is the limit as n goes to positive infinity of n plus 1 factorial divided by, well, if we distribute this, this becomes 2n plus 2. Well, 2 plus 1 is 3, so this becomes 2n plus 3. So this becomes 2n plus 3 factorial. And then since we're dividing, we're just going to multiply by the reciprocal, which is exactly what I did initially. So this becomes 2n plus 1 factorial divided by n factorial. Okay, and now you can see my n factorial goes to 1. I still have an n factorial. I still have an n plus 1 here. Okay. Now what about this one? Well, if I cancel out my 2n plus 1, my 2n plus 1 factorial, well, essentially factorials are what we do not have. And so if I cancel out that, I still have 2n plus 2 and 2n plus 3. Okay. So when I cancel my 2n plus 1 factorial, I still have a 2n plus 2 and a 2n plus 3. Okay. And so if you guys are wondering how is that possible, well, remember, what is 2n factorial? 2n plus 3 factorial. This happens to be 2n plus 1, 2n plus 2, 2n plus 3. And so when I cancel out 2n plus 1, I still have 2n plus 2 and 2n plus 3. So cleaning this up a little bit, or limit, as n goes to positive infinity, will now become, we still have an n plus 1 on the top, over now 2n plus 2 times 2n plus 3. Okay, I want you to take a good look here. Well, you can see that we could multiply these together, and if I multiply these together, I have n squared. Yeah, I'm gonna get some sort of n squared, and essentially I have n plus 1 on the top. Okay, and so the idea is that we should know by now that if the highest power is in the bottom, well, that's going to go to 0 faster. And so in fact, this limit is actually 0, which is actually less than 1. So we can conclude also that the series actually converges. We can conclude that the series actually also converges. Okay, let's look at one more. So what about this one? 2n factorial divided by n factorial, and this is where n is equal to 0 to positive infinity. Okay, well, if I take a limit as n goes to positive infinity, this becomes 2 times n plus 1. Okay, and this is all factorial divided by n plus 1 factorial times n plus 1 factorial. I'm going to divide all this an plus 1 divided by the original an, which becomes 2n factorial divided by n factorial. Okay, now simplifying this a little bit, we could see that the limit as n goes to positive infinity now becomes, well, if I simplify this, this becomes 2n plus 2. Okay, 2n plus 2 factorial. I'm going to divide that by n plus 1 factorial, n plus 1 factorial. Well, now my a, and I'm just going to simplify and multiply, so this becomes n factorial divided by 2n factorial. Okay, and so where do we stand now? Well, it seems to me if I cancel out, I could cancel out an n factorial and n factorial. If I cancel these out, I'm still left with an n plus 1. Okay, I'm still left with an n plus 1 when I cancel those out. Now for this one, when I cancel 2n factorial, I have a 1 on the bottom. When I cancel the 2n factorial from this, what essentially I will get is that I'll get 2n plus 1 and 2n plus 2. Okay, because you got to remember, 2n factorial plus 2 is 2n. 2n factorial, 2n, okay, so we need to know that 2n plus 2 factorial, that is equal to 2n. We have 2n plus 1, 2n plus 1, and then 2n plus 2. Okay, so when I cancel out 2n, I still have 2n plus 1 and 2n plus 2 left. And so when I look at this, this now becomes a limit as n goes to positive infinity of 2n plus 1 multiplied by 2n plus 2. And we're going to divide that by n plus 1 times n plus 1. Okay, now what is my limit here? What is my limit here? My limit is actually 4. This limit is actually 4, okay? And so in this case, we know 4 is actually greater than 1, which is p. Therefore, we can conclude that the series actually diverges in this case. So the series actually diverges because our p, the value that we get for p is actually greater than 1. Okay. Okay, so this is a quick way so this is the basic idea behind the ratio test.